On behalf of the School of Arts and Sciences and Penn Engineering, I am very pleased to welcome you to the 8th Annual Thomas and Yvonne Williams Lecture for the Advancement of Logic and Philosophy. We are most grateful for the generosity and vision that Tom and Yvonne have shown in establishing the fund that supports this series of lectures and that makes possible other educational activities at the university and at upper schools in our region. It was a great pleasure to work with Tom when I first arrived at Penn and to watch him develop, through the study of logic and philosophy, that clarity of mind which he has so successfully brought to bear in the sphere of practical affairs, and that sustains his ongoing passion for the life of the mind. And it remains a great pleasure to work with him now on a range of activities that will advance a general appreciation of the power of reason to clarify problems, both practical and theoretical. I am delighted to introduce this year's Williams lecturer, Dana Scott. Dana is an internationally recognized mathematical logician whose work has also spanned computer science, mathematics, and philosophy. He has made seminal contributions to automata theory, modal logic, model theory, set theory, and the theory of programming languages. He has received numerous honors and awards recognizing these contributions, one especially worthy of note on this occasion, the Harold Pender Award, given by the faculty of the Moore School to an outstanding member of the engineering profession who has achieved distinction by significant contributions to society. Dana was thus honored in 1990 for pioneering the application of concepts from logic and algebra to the development of mathematical semantics of programming languages. And now I give you my esteemed law school colleague, Bill Ewald, a former student of Dana, who will say a few further words by way of introduction. Thank you. Thanks, Bill.
So let me start by saying something about Dana's activities not as a researcher, but as a teacher. Now, I first met Dana at Oxford in the late 1970s, where he was the first occupant of the chair in mathematical logic, which, despite its name, was actually a part of the subfaculty of philosophy. Dana had already in his first 5 years there established a thriving community of logicians with a large number of graduate students and with very well-attended seminars and lectures, often joined by logicians from London or Cambridge or visitors from the United States. He had also expended a great deal of energy, not just in supervising graduate research, but in organizing the new undergraduate program in philosophy and mathematics. His teaching style was distinguished by three things. The first has to do with the internal structure of mathematical logic. Already, logic departments were beginning to specialize, putting all their eggs into the basket of model theory or set theory or recursion theory. Dana fought against this tendency. He had done deep research in each of the principal branches of logic, and he pressed his students not to narrow themselves, but to look beyond their own narrow areas of specialization. Certainly the work that was being done under his guidance, both at Oxford and then later at Carnegie Mellon, covered a remarkable range. Not just the mainstream subjects of set theory, model theory, and recursion theory, but also modal logics, tense logics, lattice theory, intuitionistic mathematics, and quite intensively at the time, sheaf theory and category theory. These things are of course related, but that was the point, to show his students how to commute between fields, to take an insight from one branch of logic and apply it to another. The second thing is a bit hard to explain without concrete examples, but the more one listened to Dana, the more one came to see that for him, the important thing was not logical technique or even results, but ideas. Not that technique was unimportant, but it was a tool and not to be taken as an end in itself. More than one of his graduate students had the experience of presenting him with the solution to a problem only to be told, your result is right, but the proof is too long. Why don't you see if you can make it a bit simpler so that we can see what's really going on? There was an insistence on clarity, on precision, on brevity, on elegance, again, not as ends in themselves, but in the service of understanding what the results meant. The third thing had to do with what might be called the foreign relations of mathematical logic. Dana had one foot in the mathematics faculty, another in philosophy, as well as his work in computer science, and he made it clear to his students that he took these neighboring fields extremely seriously, that logic could only be enriched by an infusion of problems and ideas from outside. Somewhat surprisingly, he also regularly pointed out the importance of understanding history. At the time, the fashionable tendency in Oxford philosophy was with extremely recent topics in philosophy of language and with what has been called the Davidsonic boom. Dana once quietly remarked that the philosophers could find a great deal to think about if they would just go back and read Euclid. It's not surprising these same restless intellectual tendencies, the dislike for being confined to a single field, should have manifested themselves in his own work. Let me briefly illustrate the point by mentioning three of his many awards. In 1972, he received the Steele Prize, the highest award of the American Mathematical Society, for his work in set theory, specifically for his new proof using Boolean-valued models of the independence of the continuum hypothesis. The Steele Prize is awarded for work in all branches of mathematics, and it's worthwhile to consider some of the other recipients. The previous year, the winners had been Dieudonné and Philip Griffiths. Later winners include figures of the stature of André Weil or John Milner. 4 years after that, in 1976, he received the Turing Award of the Association for Computing Machinery for his work with Michael Rabin on non-deterministic automata. The Turing Award is widely viewed as the highest award in the field of computer science, a branch of mathematics quite different from that involved with the continuum hypothesis. Here, his immediate predecessors were Donald Knuth and Herbert Simon. His work in computer science, and in particular on the semantics of programming language, Scott just mentioned, was then, some years later, recognized by the Pender Award from this school. As for the third field of philosophy, in 1997, the Swedish Academy of Sciences awarded him the third Schock Prize, the closest thing that philosophy possesses to a Nobel Prize. Here, his immediate predecessors were Quine and Michael Demmett, his immediate successor, John Rawls. These three fields, mathematics, philosophy, and computer science, have quite different problems, quite different intellectual standards, and Dana has moved at the top levels of each one. I can't pretend to know how he does it. Certainly for the many people who have had the good fortune to be his students and colleagues, both his teaching and his approach to mathematics has been an inspiration. And we are fortunate to have him here today to speak about a simple NP-complete tiling ball.
Scott, Bill, thank you very much for that eulogy. When you mention the time in Oxford, of course, gives me a lot of nostalgia for times of teaching because I've been retired since 2003. The reason I retired in computer science was that I saw that I could no longer raise any money to pay for graduate students, so that was it. But your remarks make me feel a little sad, I must say. We're certainly very happy to be here. My wife and I had no idea that it was summer. Who doesn't believe in global warming? No one raised his hand. I was going to tell you, just wait, just wait. So this is a very, very pleasant occasion to be here. Haven't had a chance to be in Philadelphia for some time. And so I have my heartfelt thanks to the departments and the sponsors for this invitation, and it's very great to see so many old friends here. One thing I need to say is a bit sad because I was looking forward very much to meeting up with Herb again, who just passed away so recently. A very great debt of gratitude is owed to Herb because my graduate student, Marko Petkovsek, as he was finishing the work on his thesis, came up with some new ideas about some special combinatorial algorithms, and then it turned out it fit in directly with the work that was being done by Herb and Doran Zeilberger. And so Herb incorporated him at once into their activities, and they published the book together, the three of them. That gave Marco a tremendous boost. He got his position in Ljubljana in Slovenia and is promoted to full professor now. And he really appreciated so much the inspiration and help that he got through Herb. Their book is entitled A equals B. I went to Amazon.com this morning and took the book search and typed in A equals B. And their book comes up at the top of the list, followed by books with extremely lurid covers in science fiction. I couldn't figure out what the connection was, but try it yourself and see what you find. A little known fact is that an earlier volume was entitled A equals A. It's long since out of print. It was only a pamphlet of 2 pages anyway, because what can you say about A equals A? A equals B is much different. It has many more ramifications, as you can imagine. So I don't know if Herb would have enjoyed my joke at the expense of his book, but I do know he's sorely missed. I also want to say that I have to confess I am a plagiarist, but don't turn me in. It was only after copying innumerable things, and I have to say, I can't live without Google and searching now. I mean, it's made plagiarism a completely new profession these days. But here's a suggestion I have, and I only thought of it after I became embarrassed with the idea that I had copied so much. What you should do is when you copy something, it's fair use, okay? But keep a note of the attribution. You can put it in another file, or you can even put it on the side of your slides. And so later on, you can tell someone where you got it. But I didn't think of doing it, but I recommend doing that. So please don't turn me in. Here's the first thing I want to point out. This is from Martin Gardner's book, where he mentions this puzzle from a long time ago by McMahon, Major McMahon. He was an army man, taught in the military school and taught mathematics, but he was also enjoyed recreational mathematics, and so he thought of this idea of making tiles by coloring the edges of the square, and instead he colored quadrants of the segments of the square like that so you could see the colors. And it turned out with 4 edges and 3 colors, you don't have 81 different kinds because you can rotate them. And so if you take the equivalence classes, there are only 24 under that. You don't turn them over, but you can rotate them. And so 24 is an extremely nice number, which is divisible in lots of different ways. And so he made a puzzle out of it. And he also did it for triangles. And, you know, that it turned out to be 24, I looked at Polya's theorem, other things, I couldn't see a general principle why 24 would come out there. There might be, but it's a very nice number. And so you can do a 5 by 5 square with the center removed, and his principle is the perimeter of your figure should be all the same color. And then when you put the tiles in the middle, matching edges should have the same color. And so you see a solution for the square. There are many, many solutions for the 6 by 4 rectangle. And amazingly enough, for the triangle with 4 colors, there are 24 different triangles, and they can be fit together too. McMahon also did colored cubes. That's a much, much more difficult puzzle to work with, and I didn't want to go into any more of that on this talk. This was just to introduce the idea of tiling in some ways to match things together. Now, back in the early 60s, Wang, who I'm sure many of you remember, was very interested into a problem about tiling where he had similar kinds of things, but we have to be careful. When we make tiles to tile the whole plane, don't allow rotations, because if you just take one tile and rotate it around and put it together and then replicate that over and over again, one tile will easily fill the whole plane. But if you don't allow rotations, then it's harder to see how to do it. And Wang thought that, well, he raised the problem. Is it decidable whether a given finite set of tiles, using, of course, many copies of the same tile over and over again, whether a finite set of tiles was adequate for tiling the plane? He raised that question there. And he thought he had proved something because he thought he could show that if a finite set of tiles does tile the plane, you can find a tiling that will be periodic so that the pattern will repeat over the thing. However, it's not true. In '96, it was proved that this set of tiles tiles a plane. I can't show the whole plane, but we're doing pretty well there with those. That set of tiles, any tiling must be aperiodic. It's a little bit related to the Penrose tiles. There are many variations on these kind of things, but I think it's quite amazing there that such a simple set of tiles forces non-periodicity. Already in '66, Wang published his conjecture in '61, and in '66 it was proved that the question of whether a given set of tiles can tile the plane is recursively unsolvable. And then later on, when complexity theory was developed, it was shown that if you're trying to tile an n by n square, that the question about whether a given set of tiles can fit into a square, no conditions on the boundary, just whether it can fit together with matching edges, that is NP complete. So in other words, that's the highest degree of complexity for those kind of problems. And of course, there are many variations on these kinds of theorems. Here's a kind of tile that I'm very fond of. I learned about it from Martin Gardner in the first place, and then Golem wrote a very fine book on Pentominoes with many, many different properties of them. So again, it's an amazing thing. If you make a domino, that's two squares put together, and of course, by turning, there's only one domino. But if you put more squares together, then different shapes arise. And so if you put 5 squares together to make Pentominoes, it's amazing that there are only 12 different ones. And so 5 times 12 is an extremely nice number that also factors very much. And so you see in the black area there, you can tile various rectangles to get 60 square units in various ways there. Don Knuth asked the question, what happens if you don't allow the tiles to be turned over? They can be rotated, but they're only one-sided. And so you need, you can't make a reflection there. You need 2 copies of the things that can't be rotated one to the other. And so he did very clever algorithm for finding the solutions for the rectangle that you see there, the 3 by something or other, with 46 solutions. He has a very nice paper on that. But he couldn't do the larger rectangle there with his algorithm. A chap in Germany on a more powerful machine was able to find out that there are more than 10 million solutions to the rectangle that's shown there. Back in '58, on the von Neumann machine in Princeton. That's really ancient history. That was the last year that the von Neumann machine was still running there. The Institute for Advanced Study never really wanted it, and they gave it to the university. Then the university discovered it costs a lot of money to keep it running, so it only ran for a couple of more years. So another graduate student and I, Hale Trotter, worked on doing the puzzle of how many solutions are there for the 8 by 8 square with the center removed. And it turned out that there weren't so many solutions. Professor Schwarzschild in astrodynamics was extremely angry with us for wasting so much time on the machine because he wanted to do calculations. Of course, now a laptop is far more powerful than the von Neumann machine. That's a long time ago. I was extremely sad to go to the Smithsonian Institute and see the guts of the von Neumann machine sitting there. It's like looking at a corpse because you have no idea what it was like when it was humming away. It had an electrostatic memory, and you know what Princeton is like with the humidity there, so it was best to run the machine at 3 o'clock in the morning. It was much more reliable then. And that's written up in Gollum's book about Pentominoes. So those are fun things, and I think it's really remarkable that a simple rule for making patterns allows you to then fit tiles together in such regular shapes. So now here is my conjecture, and I hope I don't live to see it either disproved. I hope I don't live to see it disproved. I wouldn't mind living to see it proved. But you see, the examples that I showed before as just one particular rectangle, and so you can always systematically decide just by trying all possible combinations, and it's finite, whether you can or cannot tile them. I mean, and that's what we did. We just systematically went through different positions, backtracking when we got into troubles until we found a solution, and you can actually then find all the possible solutions. But that's a completely finite problem. In order to have a problem of higher complexity, you have to have an infinite number of questions. So here's a way to make the Pentominoes into an infinite number of questions. Choose a number n, say a large number, and divide it into 12, partition it into 12 pieces. And then the rule is you can use M1 of the first piece, M2 copies of the second piece, M3 copies of the third piece, and so you try to make a 5 by n rectangle out of those with those numbers. Now, in playing with this puzzle over many years and wasting a lot of time, of course, you discover that sometimes you see some combinations, and that helps you then make other solutions, but an awful lot just reverts to trial and error. And you see the pieces are very much unrelated to each other. So the fact that they can fit together into a rectangle is certainly not obvious to me. Of course, this is an NP problem. NP means non-deterministic choice there. They're always, if there is a solution, you can choose something and get it. But if you're trying to systematically find the solution, it's much harder. And so here is my nefarious problem. You see, it requires some search to do it. In my experience, to ever do one of these puzzles requires some search. But it would be amazing, because it's such a restricted problem, if it required the maximum amount of search there. So my conjecture is, this is a problem that's intermediate between P and NP. So please let me know if you come up with something, but not too soon. Of course, there are many other geometric things. I love hyperbolic geometry. Hyperbolic plane can be filled in many different ways compared to the Euclidean plane, so there are all kinds of puzzles there. And of course, we could go on to higher dimensional geometric configurations too. So there's lots of area here to explore tiling things. A very old problem is the mutilated checkerboard and tiling with dominoes. That's just a single piece of two adjacent squares. And so the question is, if you take the checkerboard without the diagonally opposite corners, can you tile it with dominoes? And the answer, very easily to prove, is that you can't do it, because if you just colored the checkerboard the way you usually see it, if you look at the diagonal corners, they're the same color. And so if you remove them, if you remove the black squares there are more reds than there are blacks. But every domino covers one red and one black. And so therefore, if you covered the whole board, there would be the same number of red and black. And so that's impossible. That's an old, very old observation. I want to give you an algebraic deduction of this observation. You see, in order to do it the other way visually there, you had to remember the red and black coloring. Of course, it's easy to remember that, but you had to choose to add some structure to the problem in order to see the answer here. So now I want to show you a way for discovering what you need to add there without really doing much in the way of thinking. So first of all, we're going to code the coordinates of the squares in the 8x8 checkerboard by using monomials. That is, the exponents there are the coordinates of the various squares there. In fact, we could just add all the monomials together and make a big giant polynomial, and as a data structure, that contains all the information that we're thinking of all those squares. That polynomial, we could call it a shape polynomial. It gives us the shape of the 8x8 board. Now, if you think of dominoes, a vertical domino is the polynomial 1 plus x. 1 and then an increment in the x coordinate. I'm counting from the top here and the matrix counting here, going down x here and y that way. And the other one represents a horizontal domino. And now if you multiply a domino by a monomial, all you're doing is translating the exponents over to the starting at the corner ij. And so therefore, if you take a polynomial and multiply it into a domino, that means you're taking lots of copies of the domino and putting them all together. So the problem of covering the checkerboard is exactly, and now I've taken the mutilated checkerboard with the diagonal corners removed, the checkerboard polynomial minus the diagonals there can be covered if and only if you can find polynomials for giving copies of the two dominoes such that when you multiply out the polynomial, it's equal to your checkerboard one. Okay? So this is just a restatement using the simplest laws of exponents from algebra there. That's equivalent to the problem. Now I ask you, does that equation have a solution in polynomials p and q? Now if you look at that polynomial, you'll say, wait a minute, I see a root of the polynomial on the right-hand side. That doesn't take any thinking there. minus 1 is a root on the right-hand side. And you can easily check that minus 1 is not a root on the left-hand side. Of course, using minus 1 and taking monomials with the exponents, that's exactly the checkerboard coloring of the thing. So this is the same proof, but you see I discovered it by algebra. And you can do many other problems by algebra as well with other properties of polynomials. These are polynomials with non-negative coefficients. And I have more to say about non-negative coefficients in a minute here. I thought of that wonderful proof, but then I discovered it's been known for a long time. First, I found it in the book by Stein and Chabot, but then with some search, I found that it's been known for a long time, and I'm sure it's been known for even longer. But then I thought, maybe there's a problem here in general. The checkerboard is only one problem, and that turned out to be negative. It didn't have a solution. But if I suppose I give myself, and I'm going to use three-dimensional pieces or polynomials in three variables. Suppose you give yourself a fixed set of tiles, polynomials, t1 through tn there. If you pull out of your hat a polynomial p, you ask yourself, do there exist coefficients, the q's, to solve that equation? So each p, a shaped polynomial, represents a different problem. So we have infinitely many problems here. And so, of course, the question about whether there's exactly systematic way of solving all of those problems, say with a polynomial time algorithm, is the question about whether this is a difficult question or not. And so I was able to prove, and maybe someone has done a similar thing. I did some searching. I didn't find something exactly similar. There is a fixed set of polynomials for which, given p, the existence of the q is an np complete problem. And I'm going to show it visually here by using three-dimensional shapes, dominoes. So I had various different ways of doing it, but finally I realized I could reduce the satisfaction problem of Boolean formulas, which is one of the first ones to be proved to be NP complete. I can use the satisfaction problem for Boolean formulas as the example of the NP complete problem, and I can reduce the tiling problem to the Boolean problem. Now, how are you going to represent the truth values, true and false? I thought of several different ways of doing it by different shapes. And then once in the middle of the night, I said, wait a minute, what about water pipes? Suppose you take a path that's just one square thick there. Yes? I made two closed paths here. And now if you space them properly there, you see what I've done with the dots there. I've put a dot at every other coordinate on the coordinate paper there. And so if you space the things properly there, it happens that if you just place one domino, then everything else is fixed all the way around, and there are two different kinds of flow, either an even flow or an odd flow. So you see the even flow starts with the corner at one of the dots, and then everything is fixed going around there. But you have to space the things properly there so you don't mix up even and odd. And if you, instead of choosing the first domino right in the corner, you choose it in the middle, then you get an odd flow. And so the flow indicates a choice of even or odd, true or false there. So I'm going to use that kind of configuration to represent the truth values. Now what I do is I make a large apartment building with steam pipes in it, with lots of flow going through the apartment building. Originally, we'll have several different circuits corresponding to the variables in the Boolean formula. So P0, P1, P2, and you can have as many as you like. So think of those as just strips going down and coming back, a circuit there. One circuit for each variable. And now what we do is we send off things, we divert the flow as necessary over to the right-hand side there to service each one of the clauses of the Boolean formula. Now, it's a very nice exercise that even students can do to show that the problem of satisfaction of Boolean formulas, if you do it in conjunctive normal form, a conjunction of disjunctions, okay? By introducing additional variables, each one of the conjuncts only needs 3 variables. It's an elementary exercise to do that if you figure out the trick of introducing new variables to represent the subformulas of the formula. Okay? And so each flow is diverted in 3s depending upon the nature of the clause. But some of the variables have to be negated. So I have to alter the flow in the diversion there to change even to odd or odd to even. And you see, once you set one domino at the top of the yellow things there, everything is going to be determined. And so that's the choice of the valuation for the propositional variables. And then the structure of this set of pipes here tells you exactly where you are taking the information that's coming out of the flows. Now we need to be able to check that the clauses are true, each one of the clauses are true. So on the far right-hand side there, you have to put a bracket around which one of the terms you want to turn out to be true. And if you can find out so that everything is bracketed properly there and the flows are flowing, then that means in every clause one of the terms will be true, and so that means that the whole Boolean formula is satisfied. Simultaneously, all of those disjuncts are true, and that's the satisfaction problem. But how did I get the negation to work out there? What I needed to do, and this is where 3 dimensions come in, I treat this like the elevated railway here. The blue diversions are moved up 2 units so that they flow over the top of the yellow ones there. So I have to do this in 3 dimensions. And so at that corner where they're diverted, I stick in a block there that diverts even flow to odd flow, and then when it comes back, it diverts odd flow back to even flow, or the other way around. So you just need 2. See, I have certain registration squares where things can only fit in if they're one of the significant checkers there. And I just have to have a 3-dimensional configuration there that will either change the flow from even to odd to even, or the other way around. And so you see, I only need the domino itself to make the flow, and in 3 dimensions you have horizontal, vertical, and up, sticking up. There are 3 different axes there. So there are 3 dominoes for the flow, there are 2 dominoes for negation, and there are 3 dominoes, or multi-ominoes here, for checking which one of the clauses turns out to be true. So I needed only 8 specific configurations altogether to do this, to have a tiling problem that's equivalent to the Boolean satisfaction problem. And so that's the idea. Okay? And you see, this is the problem that could be stated algebraically. I could write down exactly what those polynomials are, and now we have this problem. This is algebra without minuses. Plus and times 0 and 1, but that's all. Okay? And that's an interesting algebra. And there are other questions you can ask about that algebra. For example, many years ago, Bill Lavier pointed out that in algebra without minuses there, that first implication is true. And now you see these quantities without minus could be cardinal numbers in various categories, like the category of sets. And so, I'm about to fall off the thing here. The first one says, suppose you have a set X that's equivalent to, in cardinality, an isolated point plus its Cartesian square. It's very easy. You can make the natural numbers in a one-to-one correspondence with 1 plus n squared, for example, with a squaring function. There are many sets that will satisfy that in cardinal numbers. And now what was discovered was that that implies, just by algebra alone, that x is equal to x to the 7th power. Andreas Bloss wrote a very amusing essay on 7 trees from 1 on that. So when I got a hold of a very nice, this Waldmeister equational theorem proving that can run easily on a laptop, there I thought I would try that out, and it worked out. It takes many steps to actually do this proof, but an equational theorem prover could discover the truth of that statement there. And so then I thought, hey, I'll try some other ones. So I put in some other different hypotheses and got out those answers, and I looked at them and I said, wait a minute, roots of unity. The things on the right-hand side there correspond to root of unity in algebra, but we think of that in commutative algebra with minus there. Of course, the irreducible polynomials that the roots of unity satisfy, the cyclotomic polynomials, are very interesting set of things. Their coefficients are mostly plus 1s and minus 1s, and only much later on do other coefficients appear there, but they're all nice integer polynomials there. And so by moving the minuses to the other side and moving things around, you can make up a lot of different hypotheses without using the minus sign. But I couldn't find the right answer to that. I have to leave that as a question there. I'm sure the cyclotomic polynomials have something to do with this, but I didn't find any other good examples of these equations here. But what this shows, because there are so many different interpretations of algebra without minus, and many different kinds of categories where you have products and coproducts and the distributive law there that give you the algebra there. There are many different ways in which these are widely applicable truths that says if one equation is satisfied, then another equation is satisfied. So I hope someone will look into that and find a general theorem about it. I'd like to end today with a quotation from another dear friend who passed away recently, much to the sadness of numberless friends, family, and associates. He said, mathematics enables us to understand things if you can formulate things in a beautiful way so that you can appreciate how it all fits together. And I very much believe in that and leave you with that thought today. Thank you so much. I'll be happy to entertain a question. Please.
But this may not be relevant. In the three polynomials, T1, T2, T3, three variables,
Yeah.
the existence of which gives you an NP-complete problem.
Yeah, I needed 8 polynomials. Needed 8 polynomials for that. 3 variables. This example I did in 3 variables. I could do it in 2 variables.
Oh, yeah, okay.
But it takes many more polynomials.
Okay, let's take those polynomials.
Yeah.
There's something special about the ideal they generate in the real polynomials.
You would think so, but algebra without minus doesn't work the same way as classical algebra does. And that's why I couldn't get anything out of Buchberger's algorithm or those things, you see, because it's really quite different without minus. You see, I mean, the Buchberger's algorithm shows that it's a polynomial problem to solve the membership and ideal thing. But that takes the full power of commutative algebra. So there's something else there. But I'm sure that those examples that I showed you related to the roots of unity, I'm sure there's something broader happening there. You can't have 3 examples like that without having a more general one. I mean, what would mathematics be if you were stuck with things like that? Yes, so. By the way, if someone can trace it down, I found in plagiarizing things, I found a quotation from von Neumann, but I don't know where it occurred or why he said it. He said, "In mathematics, you don't understand things, you just get used to it." I mean, he was awfully clever at getting used to things, but I don't know why he said that. Other question? Thank you for coming today.